How will the universe end? The answer will shock you more than a sci-fi movie. Every night, when we look up at the star-filled sky, we are witnessing a grand play, a cosmic light show billions of years in the making, generously gifted to us by the universe. Those twinkling points of light, those distant spiral galaxies, seem eternal, symbols of permanence. But this is just a beautiful illusion created by the brief timescale of a human life. The reality is far stranger and more astonishing than any science fiction film. Every ray of light that reaches our eyes, from the sunshine of day to the gentle light of the moon, is one of the first signs of an inevitable conclusion, a final silence that awaits at the far edge of time. We often think the stars will always exist in the night sky. But have you ever wondered, if one day everything were to disappear completely, what the universe would be like? I'm not talking about a few hundred or a few thousand years from now, but a span of time so vast it defies human comprehension, tens of trillions upon trillions of years into the future. By then, not only will the stars have gone out, but even time itself may lose its meaning. And more astoundingly, the very laws of physics we hold as the bedrock of reality could collapse. Does it sound fantastical? Yet all of these scenarios, from the evaporation of black holes to the decay of matter itself, are not products of imagination. They are calculated by theoretical physicists using rigorous formulas, elegant mathematical equations, the results of extraordinary efforts to understand the ultimate fate of everything. The Golden Age, a festival of starlight. Right now, we're living in the luckiest, most brilliant phase in the history of the universe. This is the stelliferous era, a time when the cosmos is like a city that never sleeps, glittering with the light of trillions of stars. We are the audience watching this grand performance, completely free of charge. But like any great party, it cannot last forever. Stars are a luxury item in the universe. They are colossal fusion reactors, consuming a finite fuel source, hydrogen gas, which was created only once in the primordial moments of the Big Bang. Like a campfire, when the last logs burn out, the fire will die. When the hydrogen fuel is depleted, the stars too will come to the end of their lives. In 1930, a young Indian physicist named Subramanian Chandrasekhar, during a long sea voyage from India to England, performed a calculation that would shake the world of astrophysics. He discovered a stark yet poetic truth. The fate of a star is determined at the very moment of its birth, based on one starting factor, its mass. Not its brightness, not its color, not the number of planets orbiting it, but its initial mass seals its unchangeable destiny.
The destiny of stars, from red giants to diamond tombs. Let's take our own sun as an example. As a medium-mass star, in about 5 billion years, when its core runs out of hydrogen, it will begin to fuse helium. This process will cause its outer layers to swell monstrously, turning it into a red giant. In this phase, it will swallow the nearest planets like Mercury and Venus. Earth, though it may not be completely engulfed, will be pushed outward and scorched by the intense heat. Our atmosphere and oceans will boil away, leaving a dry, barren, lifeless planet. After passing through its red giant phase, the sun will shed its outer layers, creating a beautiful planetary nebula. What remains at the center will be an ultra-dense, intensely hot core about the size of Earth, known as a white dwarf. It is, essentially, a giant diamond tomb containing the remnants of a star. It no longer generates energy. It will simply cool down over trillions of years, eventually becoming a cold, dark black dwarf. For stars much larger than the Sun, from 8 to 20 times its mass, their end is far more spectacular. When their fuel runs out, their cores collapse under immense gravitational pressure, triggering a horrific explosion known as a supernova. In a brief moment, a single supernova can release more energy than an entire galaxy combined. This explosion seeds the cosmos with heavy elements like iron, gold, and silver, which become the building blocks for the next generation of stars and planets. What remains after the explosion is a bizarre object called a neutron star, a sphere of matter only about 20 kilometers in diameter, but so dense that a single teaspoon of it would weigh 11 tons. And if the initial star is even more massive, its core will collapse completely with nothing to stop it. It will become a black hole, a singularity in space-time where gravity is so strong it can bend space and swallow light itself. The age of black holes, the slow evaporation of giants. When the last star in the universe has burned out and faded, the cosmos will enter a new, dark and cold era, the degenerate era. The sky will no longer have starlight, only the remnants, black dwarfs, neutron stars, and black holes drifting in the silence. Many people think of black holes as greedy monsters, actively hunting and devouring everything. In reality, they are quite passive. Unless matter gets too close to their event horizon, they can exist for hundreds of billions of years doing nothing at all. But black holes do not last forever. This was one of Stephen Hawking's greatest discoveries. By combining general relativity and quantum mechanics, he proved that black holes are not completely black. Due to quantum effects at the event horizon, they emit an incredibly faint form of energy, now known as Hawking radiation. This process causes the black hole to slowly lose mass and eventually to completely evaporate. This process is incredibly slow. The larger the black hole, the slower it evaporates. For example, a black hole with the mass of our Sun would take 10 to the 67th years to disappear. The supermassive black hole at the center of our Milky Way galaxy will take up to 10 to the 100th years, a 1 followed by 100 zeros, a number vastly larger than the current age of the universe. And then one day, in the absolute silence of an empty universe, the very last black hole will evaporate in a final flash of gamma rays, without a sound, without a trace. The universe will then enter its black hole era, and finally, the dark era. The decay of matter, the death of the atom.
But the story is still not over. After the last star has died and the last black hole has evaporated, the universe will still be left with fundamental particles like protons and electrons, the bricks that built everything we know. It would seem they are eternal. Not quite. In the 20th century, physicists like Abdus Salam and Sheldon Glashow developed grand unified theories, attempting to merge the fundamental forces of nature. One of the astonishing predictions of these theories is the proton, the nucleus of the atom, is not perfectly stable. They can spontaneously decay, but their lifetime is extraordinarily long, around 10 to the 34th years. This number is so vast that over the entire 13.8 billion year history of the universe, the chance of a single proton decaying is virtually zero. But if you have an infinite amount of time, the nearly impossible will eventually happen. Gradually, in the cold and darkness, one proton at a time will decay into lighter particles. No hydrogen atoms will remain. No matter. The universe will then become a near-perfect vacuum, filled only with a faint and frigid sea of radiation, approaching a state of heat death. You think a vacuum is empty? Not exactly. In quantum physics, a vacuum is the state with the lowest possible energy, but it is still teeming with quantum fluctuations, pairs of virtual particles constantly popping into and out of existence. And here is a terrifying idea. Scientists suspect that the current vacuum state of our universe may not be the true, stable state. It might only be a false vacuum, like a ball resting peacefully in a divot on the side of a hill, but not at the bottom of the valley. If a large enough quantum fluctuation were to occur somewhere, or if quantum tunneling took place, a bubble of true vacuum with a lower energy state could form. This bubble, with potentially entirely different laws of physics inside it, would begin to expand in all directions at the speed of light. It would erase our entire universe as it passed through, restructuring space-time and matter without warning, without a sound. We would never see it coming. And the most frightening part is, theoretically, this could happen at any moment, anywhere, though the probability is considered to be extremely, extremely low. when all is said and done, no stars, no planets, no atoms, the universe is empty, dark, and silent, approaching maximum thermal equilibrium. You think that is the final, definitive end. Perhaps not. In the strange world of quantum mechanics, randomness always reigns. Even in a near-perfect vacuum, there are always quantum fluctuations, pairs of virtual particles constantly popping into and out of existence. And if you wait long enough, a truly infinite amount of time, these random fluctuations, in theory, could create anything. They could spawn a new universe in another Big Bang, or they could create something even stranger.
The physicist Ludwig Boltzmann proposed a controversial idea. If you wait long enough, a collection of particles could randomly assemble into a complex structure. For example, a complete, functioning human brain, complete with consciousness and even memories of a past that never existed. This is known as a Boltzmann brain. This presents a terrifying philosophical paradox. In the far, far future of the universe, the probability of a brain like this popping into existence for a fleeting moment from quantum chaos might be greater than the probability of an orderly universe like ours forming and evolving conscious beings. The universe then might just be an empty space, where lonely, disembodied consciousnesses flicker into and out of brief existence. Time itself would become meaningless, as there would be no change, no evolution, only the eternal recurrence of randomness. Hearing all this may sound terrifying and nihilistic, but let's not forget one miraculous fact. We, humanity, a tiny species existing on a speck of dust orbiting an ordinary star in an ordinary galaxy, have the ability to comprehend all of this. Using mathematics and physics, we can write the story of the past and future of the very universe that gave birth to us. Perhaps the universe spent hundreds of billions of years to arrange everything, from the physical constants to the formation of heavy elements, just so that we could emerge, look up, and try to understand it. We are the lucky audience, living in a glorious moment of a universe that is on its way to fading out. And maybe the true meaning of humanity, in the grand and somewhat absurd tapestry of the cosmos, is simply that we can be aware of its existence, and our own. We are the universe's way of contemplating itself, and that, perhaps, is an extraordinary privilege